Let's now go straight to this work here. The empirical formula and molecular formula. Who else hasn't come back? They will find us on the way. Okay. Empirical formula. This is the simplest formula of a compound which expresses the ratio in which different atoms present in one molecule exist. This is the simplest formula, the simplest. This one you can derive it. You will be given certain conditions under which certain substance is, and then they will give you to derive the empirical formula. So whichever ratios you get, you'll use them to calculate the empirical formula of that substance. Now, you get them in form of ratios. Like maybe carbon might be having 1, hydrogen is 2, oxygen is 5, all that, we need them here. So examples of these things include 1, this is the molecular formula. Then this is the empirical formula. Water, this is its formula and remains that way. When you look at ammonia, it is this, it remains like that. Ethene is like this, but the empirical formula, you get it like this. So when you get a number like this, in the organic compounds, we don't have any substance that has CH2. 2 can never be like that. So for a carbon atom to be satisfied, it must be attached to other 4 elements, Now here, this one is telling us that there are only 2 hydrogens. This one shows that there's something lacking. So the number you get times the empirical formula gives you the molecular formula. So here they are saying steps in calculating the empirical formula. Number 1, write down the symbols of the elements present. These symbols will be given in an equation. Write them the way they are. 2, write the percentage composition of each element by mass below the symbol. So if a symbol is C, here, if the symbol is C, below C, you write this percentage. Maybe it is 80%. 80%, that's what you do. This is percentage composition. Hydrogen can be like 12%. Then others, we shall see how they happen. So this is what they mean. Write down the symbols. The symbols we have written. The symbols we have written are this one, C and H. These are our symbols. Symbol. We go to percentage composition. After this, find the number of moles of each element by dividing percentage composition by the relative atomic mass. Like in the table, carbon is 12, hydrogen is 1. So we find the moles present, by dividing this 80 by 12. Each element has its own relative atomic mass. Hydrogen is 1. So this one, divide this by this, you get 80, divide by 12, you get 6.66. You write it to 3 decimal places if there are many. If not, you write it the way it is, 12, like that. So here you have now, these are the mole ratios. The moles in that substance. Now, find the mole ratios of each element by dividing the moles with the smallest number. So here we are going to look for mole ratios. Like here, 6 and this is the smallest. So we're going to divide 6.667 by 6.667, and then 12 divided by 6.667. So now these are the mole ratios we have. Here we shall have 1, 2, 12 divided by 6.67, you get 1.8. 1.8. Now, when you find this type of answers, the condition is if the mole ratios is in fraction, round off to the nearest whole number if it is close to the whole number. Now, if this one was 1.5, this one is very far from a whole number. 1.6 is very far. But 7, 8, actually 8, 9, 1.8, 1.9, these are close to a whole number. So the closest whole number here is what? Yes? The closest whole number from this one is? It is what? The closest whole number. Shina? 1.8. What is the closest whole number to 1.8? Two. Is 2. Thank you very much. So here we round off this to 2. So the thing remains as 1 to 2. That is what happens. Now there is another condition we are going to look at here. Condition 2 says multiply if the fraction is far below, multiply by the small number that converts the fraction to the whole number. If the fraction is not close to the whole number. If the fraction is not close to the whole number. Let's take an example here. You go to 1.5 to 1 here. This one is very far. It is far from a whole number. You get it? So if you get a number that can multiply this by these numbers to give you numbers that are whole numbers. What do you think we can use here? The smallest number possible. If you use 1, it remains the same thing. What about when you use 2? What does it come to? This one becomes 2 and what? 2 to 3.
2 to.
That is the way you decide with these numbers here. Okay? So let's look at an example. Now this one, before we go to an example, I want to clarify something on this molecular formula. If empirical formula in short is like this, if you want to get the molecular formula, what do? Now you have reached here. This is your empirical formula, isn't it? You want to get this. What you do, you get any number. Any number times any number. Let's represent that number by n. You can also pick your own letter, maybe x, w, as long as it is a certain number, you know. So that number times the empirical formula will give you the molecular formula, isn't it? Yes? Yes.
I didn't understand whereby you round off, like you were saying, 1 is like where 1 is 2, 1.8.
Yes.
Where you round, you were saying.
Now here at this step, you see this. We got a number that has this 6.667 and then 12, isn't it?
Yeah.
Now, if we divide by the smallest number, we are getting the mole ratios. This one comes to 6.667. This one comes to 6. We are dividing by the smallest. You divide for me this, you get 1, isn't it? What about when you divide this? What do you get? Yes?
It's 1.8.
This is 1.8. Now, from this condition here, if the mole ratios is in fractions, these are also fractions. 1.8 is a decimal, but if you can convert it to a fraction, you get it. So now here, round off to the nearest whole number if it is very close to the whole number. Now this 1.8, 1.8. The next number is 1.9. These are very close numbers to a whole number. They are very close. Okay? So here we don't need to look for any number to multiply with, maybe to bring us to the closest answer. Here you don't need to struggle. You just say this is roughly 1 to 2. You get it? Because they are very close, you just round off this number here alone. 2 to 2. Now, if you divide and then the number is below, like from 1.5, you are going backwards, what should you do? This is where you come in. This is where you come in with the second option here. You multiply by the smallest number that converts the fraction to the whole number, if the fraction is not close to the whole number. Is it clear?
So how about like instead of us having 8, we have like 1.6. Now, will you surround it off to a whole number? That is us 2.
And now the number is as large as this. Starts from 1.1, isn't it? To 1 point what? 1.9. So the next number is 2. This is 1 below here. You get it? So if it is 1.1, now you have reached in the middle, it's 1.5. You see, now when it comes 1.5, this one you can multiply and get exact number that is even very close to the what? That is, you get, when you multiply this by any number, it gives you exact number. You get it? But now, if it comes to 1.6, 1.7, 1.8, 1.9, these are very close to a whole number this side, isn't it? Yes?
Yes.
These ones are close to a whole number. So what you do, you just round off to the whole number. But if it is from this side to this way, make sure you look for a number that when you multiply, it gives you the closest answer to this. Okay? Yes?
Yes.
Okay. Now we are going to take an example here. We are going to take an example. They are saying, calculate the empirical formula of the compound containing 80% carbon and 20% hydrogen. Okay? The number has, this is carbon, this is hydrogen. What is the percentage composition? It is 80 to what? To 20. So now this is the percentage composition. The next step is to look for the what? Next step here, to write down the percentage composition. Number, to find a mole, find the number of moles by dividing by the relative atomic mass. Relative atomic mass of carbon is 12. One of hydrogen is 1. So carbon is 80 divided by 12. Then we shall have 20 divided by 1. This one divided by this, you get 6 point what? Yes? 6.667. Then 20 remains. Now, these are the moles. The moles here, finding the number of moles. Now, if you want to find, the next step is to find the mole ratios to which these elements react. This and this. What is their mole ratio? We divide by the smallest number we are seeing here. It becomes 6.667 divided by 6.667 mole ratio to 20 divided by 6.667. If you divide this, it comes to 1. When you divide this, what does it come to? Yes? Peace. What is
3.
the answer? It is 3. You get that? Now these ones are automatic. It shows that carbon is 1, hydrogen is 3. Now this is very less. We don't have any hydrocarbon that has this kind of numbers. Because carbon to be full, it must have 4 elements joined to it. Now it shows that this carbon atom has only three elements. That is hydrogen. You find hydrogen here, you find hydrogen here, you find hydrogen here. Where is the other one? It is not there. So that's why they call for molecular formula. Okay? We find it from the relationship that, let me show you how it comes about. It is here. Molecular formula, it is the empirical formula times any number that we don't know gives us the molecular formula. Now, when you look at this number here, they say B part, if the molecular mass of the compound is 30, the molecular mass of the compound is 30 grams, determine it is molecular formula. Now, they have given us the molecular mass. What is the molecular mass? Yes? From the question, what is the molecular mass? It is 30, isn't it? Yes?
Yes.
So from this empirical formula, you can also calculate the molecular mass of this substance we have got. It's going to be CH3 times N, which is equal to 30. Now, here, C is what? C is 12 plus hydrogen, which are 3 times 1 into N is equal to 30. So this one is going to be 15.
Yeah.
15N is equal to 30. So N is what?
2.
2. So this number times the empirical formula is going to give us a molecular formula of that substance. So we shall get CH3 times 2, which is the same as C2 H what?
H6.
H6. Now this one is going to satisfy a condition that carbon has 4 atoms joined to each other. There are 2 carbons. So we shall say 1 carbon and then another carbon. They are joined together. 6 hydrogens. If you put here, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. How many hydrogens are these?
6.
So 1, 2, 3, 4, 5, 6. If you look at this carbon atom, it has 4 elements joined together. We have this, we have this, we have this. Then there is this one, it is using to link to another carbon. Okay? Even this one, it has 1, 2, 3, and then this other one, which is used to link to the other carbon. Meaning carbon has 4, this one also has 4 electrons combined. Is it clear? So that is what you do. Now here, they are telling us to calculate the empirical formula of a compound containing empirical formula of the compound containing, we have iron, isn't it? What's the percentage of iron? 20? 28. 24% what? Sulfur. Sulfur is 24. The rest being oxygen. The rest being what? Oxygen. What is the remaining? The rest is what? What is the rest? That fraction, that is the rest. Someone get for me the answer. How do you get it? What is the total percentage? Total percentage.
58.
The total percentage is 100. So if you add this plus this minus 100, the rest, the remaining one is for oxygen.
48.
It is 48. Okay. So let's continue. If iron is 56, sulfur is 32, oxygen is 16. Get for me the moles here. Get for me the moles. Get for me the moles. What are the moles of iron? To 3 decimal places. This is percentage composition. The moles. What do you do to get the moles? You divide what by what?
Percentage by the
Percentage by the relative
moles.
atomic mass, isn't it? Yes?
Yes.
Percentage by the relative atomic mass. What is the answer here?
0.5.
0.5, exactly.
Yes.
Yes.
Okay. This one?
0.7.
0.7. Yes?
5.
I do what? Please speak up. Speak up. I don't want to leave you behind.
Repeat.
I repeat. We are following these simple instructions here. When you are writing empirical formula, you first write down the symbols of the elements present. The symbols of the element what? Present. They gave us iron, they gave us sulfur, the rest being oxygen. That's what we have here. You get? Now, write down the percentage composition by mass. Percentage composition, they gave us iron is 28, sulfur is 24, the rest being oxygen. We calculated it from here, that the total percentage is 100. The one of iron is 28, the one of sulfur is 24. If I add these 2 minus 100, the rest will be for what? For oxygen, isn't it? Yes? Esther?
Yes, teacher.
Are you listening? Was it you or someone?
It was Patricia.
Patricia? Patricia?
Yes.
Okay, be attentive now. So here we are saying, now after getting this, we are going to find the number of moles of each element. You get the number of moles by dividing the percentage composition by the relative atomic mass. You get it? The relative atomic mass of iron is 56. The relative atomic mass of sulfur is 32. The relative atomic mass of oxygen is 16. Is it clear?
Yes.
So the percentage composition is 28. Divide by 56.
Yes.
What do you get? Is it 0.5?
0.5.
Correct.
Yes.
What is the one of sulfur? 24 divided by 32. What do you get?
0.7.
0.7.
Five.
Only 7.5. What about the one of oxygen? The one of oxygen? (48) divided by 16. What do you get?
3.
Is 3. Okay. Now we have found moles. Now we want to find the mole ratios, isn't it?
9.
Yes. When you come to mole ratios are got by getting these moles, and you get the lowest, divide by the lowest number or the lowest mole present. Now we are going to have, what one is the lowest? It is 0.5, isn't it?
Sure.
So 0.5 divided by 0.5, 0.75 divided by 0.5, then 3 divided by 0.5. What do you get? This is 1. This one?
1.5.
1.5. This one?
6.
6. Now, where is who? Was it? Someone was asking how the things come about. Who was that? So what do you do next after getting this?
Yeah.
Yes? This 5 is far from the whole number, isn't it? It is very far from the whole number. So what do?
We multiply.
You multiply by
We
what?
multiply
By what?
by
By?
by 2.
By 2.
2.
Very good. So if you multiply by 2, you get 2. This one comes to
3.
3. Then this one goes to
12.
12. So if you write down the compound, it's going to be F2 S3 O 12. Now, in the chemistry, we don't have a compound with this kind of a name. But you can simplify this one here. This is an iron, isn't it? And that iron is a sulfate, which is SO4, isn't it? Meaning you have factored out 3, then you shall put that 3 here. So this one is going to be 3 times 2, which is this. Then this times this, which is 12. Have you seen? Yes? Is it clear?
No. It's
In the
actually my network is disturbing.
It is disturbing.
Yes.
Okay.
It's stopping and
Now, the compound here that has S and O in the chemistry is only sulfate ion. Okay? So if you reach here,
yes.
they are asking for the name of the compound. You can't write for us this name. It doesn't exist. Good. But you can simplify this furthermore by factoring out 3 outside here. Okay? The common term between S and O. So what is left here is 1, which is 1S. How many 4s are left? There are 4. 4 O's, isn't it? So the whole of this is the same as this one here. Then you copy only iron 2. So what is the name of this compound?
Iron 2 sulfate.
Is it iron 2 sulfate? Yes?
3.
It is iron what?
Mm.
Iron. Then this is iron 3.
3.
Iron 3 sulfate, isn't it? Yes?
Wow.
The valency of iron is not 2.
Yeah.
This is 2 is a valence of what? A
Is that
sulfate.
it? So
Then this 3 is a valence of what? Of iron. Is it clear? Yes?
Yes.
Okay. Hope you have understood that one. So this is what happens here. Okay. There is a number here. Check number 4. Do you see number 4? Yes? Have you seen number
Yes.
4? Number 4 says, calculate the empirical formula of the compound that contains, number 1, 52 grams of zinc. Can you write down that formula? I want the answer for that number. I want the answer. Calculate the empirical formula of a compound that contains 52 grams of zinc. 52 grams of zinc, 9.6 grams of carbon, 9.6 grams of carbon, and 38.4 grams of oxygen. The values are here. This is the relative atomic mass of zinc. Zinc is 65, carbon is 12, O is 16. So the first step is start with listing the what? The elements present. Then you write their mass or percentage composition. This time they have given you mass, not a percentage composition. So in about 3 minutes, we should be having that empirical formula. try to work very fast. The relative atomic masses are there. Up, I've put them there. Try to speed up. Try to speed up.
Consider molar mass.
The molar mass of what? Our minutes are running. I've seen one answer. Cynthia, Frida, Peace. Patricia. Where are the answers? Yes. Peace. Where's the answer? You are still calculating. Peace. Did you have CLO?
It's a typing error, but it's not CLO.
It is what? ZN? Peace.
It's ZN,
Mhm.
C10, and then O3.
ZN, C10, then O3. Like that. Yes?
Yes. Yeah.
Okay. We have less than 2 minutes to go. Now, let us work this number out together. Okay? Let's work it out because I've seen one answer around that is okay. Zinc, they have not given us percentage composition, but they have given us composition by what? By mass, isn't it? Yes?
Yes.
Okay. What is the one of zinc? Zinc, they told us is what? 52%, isn't it? 52 grams. The one of carbon is 9.6. Oxygen is 38.4, isn't it? Now, from this step, you go to determining the moles. If you want to determine the moles, you divide this by the relative atomic mass, which is 52 divided by 65, 9.6 divided by 12, 3.8 by 4 divided by 16. Is it what you did? Is what you did?
Seen my mistake.
Yes.
So that is what you have. So 52 divided by 65, you get 0.8. 9.6 divided by 12, you get 0.8. 38.4 divided by 16, you get what? 2.4. Okay? 3. Okay? Now, after this, we are going to get the mole what?
0.8.
The mole ratios. Isn't it? Yes? To get mole ratios, we divide by the smallest. The smallest is 0.8. This is 0.8, 0.8 divided by 0.8. 2.4 divided by 0.8, you get what? This is 1.
1.
This is 1.
1.
This is
3.
3.
3.
So our thing comes to Z and C. It is 1, 1. Then O what? O3. Okay. Okay. If it is done, I would like you to get for me this exercise. I hope you downloaded the book. Yes. There is enough exercise here for you to do up to this part. Then next time we meet, we shall calculate masses from equations. Okay? Yes?